Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Pharmaceutical Organic Chemistry, Paper 3. We are studying in Unit 4, Heterocycles Part 2. In the Lecture 7, we are studying about Pyrimidines, Purines and Azepines, synthesis, reactions and applications. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayamprabha, MHRD, New Delhi. The topics that will be covered in this session include synthesis of pyrimidines. We will be looking at synthesis of pyrimidines from malonic esters, Bedreich synthesis, Boltzmann-Rosch synthesis, Pinner synthesis, Remfry-Hull synthesis, Biginelli reaction, and Traube synthesis. We will also be looking at purines, mainly the Fischer method of synthesis, Traube synthesis, and Bergman synthesis. In the case of reactions of purines and pyrimidines, we will be studying about electrophilic and nucleophilic reactions and aromatic nucleophilic ring opening and ring closing reactions as well. And finally, we will be looking at azepine synthesis, mainly from nitrene insertion reactions and from alkynes. Let us now look at pyrimidines, purines and azepines. So what are purines, pyrimidines and azepines? These are pyrimidines are basically 6-membered heterocycles with 2 nitrogen atoms. So the pyrimidine structure is shown here. So if you start from 1, 2, 3, these are 1, 3 dinitrogen derivatives. And when we talk about purines, these are basically 6 and 5-membered fused heterocycles with 4 nitrogen atoms. So we have a benzene like a 6-membered ring, and then we have a pyridol like a 5-membered ring. So in both the rings we have 2 nitrogens each. The structure of 9H purine is shown here. And if you look at the numbering, basically in our normal heterocyclic numbering, the ring junctions are not numbered in the beginning, but the numbering for purine is an exception. So that is why we have given here exception to systematic numbering. So the ring junction also gets the number when we are numbering purines. And when we talk about the pyrimidines and purines, these are nitrogen bases present in DNA and RNA. So when we call this as a 9H purine, so the numbering starts from the nitrogen from here and not from which is closer to the ring junction. So generally whenever we start to number heterocycles, we start from the highest or the biggest ring structure. So that means this is the 6-membered ring is the biggest one. And if you look at both the rings are having nitrogen atoms. So we have to start from the 6-membered ring having a nitrogen atom. So in that case, we actually have to start from the number 1 to this nitrogen, which is close to the ring junction. But unfortunately, that is the systematic numbering. But in the case of purines, basically the numbering for purines started with not from organic chemistry perspective, but from the biology perspective. So that is the reason biologists actually started numbering this, and this is now being accepted and being followed throughout. So that is the reason this numbering is basically the biological numbering for purines. So they started from the nitrogen number here 1. So 1, 2, 3, 4, 5, 6. So the first 6-membered ring is given all the 6 numbers, followed by the second ring. So here we went with the 7, 8, 9. So in the 9th position we have a hydrogen which is attached to this particular nitrogen. So that is why this is a 9H purine. And the names for purine of nucleosides basically ends with osine, and in the case of pyrimidines, the nucleoside they end with iodine. So guanosine, adenosine are the names for the purines, and guanidine and similar things are given for the pyrimidines. The azepines are basically 7-membered heterocycles with 1 nitrogen atoms. To lessen the ring strain, these are actually non-planar. So this is the first heterocycle we are looking at is the non-planar heterocycle, and because these are non-planar, they are not aromatic, and hence they are not react like a typical benzene units, but they react like a polyenes. Some important purines and pyrimidines are shown here. Say for example, in the case of pyrimidines, we have cytosine, thymine and uracil which are present in DNA, or actually DNA and RNA are shown here. So these are pyrimidines, and in the case of purines, we have adenine, guanine. Caffeine is another important compound which we generally drink in the coffee, and anafranil and imipramine are some of the azepines which are shown here. So these are some of the examples of purines and pyrimidines. Let us start with the synthesis of purines. So we start from the pyrimidines basically. So how do we know what is the difference between purine and pyrimidine? So the pyrimidine rings are basically you can remember like this. Pyridine ring has a 6-membered with 1 nitrogen, whereas pyrimidine has similar to pyridine with 1 extra nitrogen only. So that is the reason all 6-membered dinitrogen substitutions as 1,3 substituted compounds are basically pyrimidines. So that way you can correlate that with pyridine. So pyridine is 1 nitrogen with a 6-membered. Pyrimidine is 2 nitrogen with 6-membered. So this is the pyrimidine. So how the pyrimidine can be synthesized is given here. Starting from malonic ester and urea, when treatment within presence of a strong base leads to barbituric acid as shown here. So this barbituric acid undergoes tautomerization as shown here with the trihydroxide derivative. So here we have the keto derivative, that is the amide derivative is shown here, and here we have the phenolic derivative is shown here. This on treatment with the POCl3 the hydroxy groups are getting converted to the chloro derivative, and this chloro derivatives on zinc dust reduction leads to the corresponding pyrimidine. This is a unsubstituted pyrimidine. So in this particular case, what we are making is the parent pyrimidine only is made. The next one is the Bredrux synthesis. So in this particular case, beta diketones or beta immunoketones are basically used as a starting material. So the beta diketone can exist as a ketoenol tautomer as shown here. So these are all the two tautomeric forms which exist. When this is treated with formamide, that leads to the substituted derivative here. So when there is a R group here and R prime group here, we have R group here and R prime group here. So that is how the substituted pyrimidines can be prepared using this particular method. And there is another improved synthesis where we can actually heating formamide at high temperatures with 4,4-dimethoxyl 2-butanone. So this is basically the keto derivatives here. This is nothing but the aldehyde which is protected here. So the keto aldehyde is nothing but the dicarbonyl compound. So the dicarbonyl compound when treated with the amide derivative in presence of ammonium chloride at a very high temperature leads to the substituted pyrimidine derivatives. And formation of uracil, basically this uracil is shown here, can be formed from ethoxyacryloyl isocyanate and primary amine. So the primary amine is shown here, and ethoxyacryloyl isocyanate. So this is the isocyanate unit, and this is the ethoxyacryloyl unit. These two are present in the same compound, and when this compound is treated with an amine, leads to this particular intermediate which loses alcohol moiety to give the uracil as shown here. This is a substituted uracil, and carbocyclic nucleoside analogs of antiviral compounds can be synthesized using this particular method. So if we use this particular substituted amine as the starting material, then we get a carbocyclic analog. Basically in the nucleoside we have the oxygen, the furanol side, there is an oxygen present here. Instead of the oxygen, if carbon is present, that is what is called as a carbocyclic nucleoside. So these kind of substituted carbocyclic nucleoside can be formed using this particular synthesis. Then pinner pyrimidine synthesis is shown here. So in this particular case again, 1,3-dicarbonyl compounds are treated with amidines in the presence of a base, basically potassium carbonate at room temperature, leads to the tri-substituted pyrimidine derivatives as shown here. Next, the Rumfry-Hull synthesis. In this particular case, the condensation of alpha-butyl melanodiamide with the ethyl formate takes place. So in the presence of a strong base, this condensation actually leads to the 5-butyl 6-hydroxy pyrimidine 3H bond derivatives. As shown here, the reaction actually leads to the pyrimidine derivatives. The next one is the Bignelli reaction. So in this case, aldehyde and 1,3-dicarbonyl compounds and urea react together in the presence of polystyrene sulfonic acid at 80 degree, produces this particular derivative. And when we talk about the 3-component coupling reactions, we have 3 different units which are combined together in the presence of zinc chloride. So this is acetal, and this is ammonium acetate, and this is the enamine. So these 3 react together to give in the presence of zinc chloride as the reagent, leads to the pyrimidine derivative as shown here. Next one is the Traube synthesis. In this case, guanidine hydrochloride salt is treated with cyanoacetic ester in the presence of a strong base, leads to hydroxy, that is the substituted pyrimidine derivatives are formed. So we have 3 nitrogen coming from this particular guanidine unit, and we have 1 nitrogen coming from the cyano derivative. So that's the reason we have 4 nitrogen derivatives. So that means 1, 2, 3, 4, 4 nitrogen are present in the final product. And when we talk about reactions, basically we have to look at the resonance structures of pyrimidine. So we have 2 neutral structures, which is nothing but the Kekulé structures, and we have 1, 2, 3, 4, 5, 6 charged structures. Because of the presence of the nitrogen atom, which is electronegative, we have various charged structures are possible in resonance. So this is how the pyrimidine ring can exist in various forms, and the reaction also happens at different positions depending on these kind of intermediates which are formed in the reaction. And pyrimidine is a very weak basic, that is its pKa is 1.3 only. And we have 2 types of reaction that are possible in the case of pyrimidine. One is the reaction at nitrogen, another one is reaction at carbon. In the carbon reactions, basically it can be an electrophilic substitution or a nucleophilic reaction. Both are possible on the carbon. And of course, quaternization is one example of the reaction at the nitrogen. So this pyrimidine can be reacted with methyl iodide or trithoxyborate as shown here. So these 2 are the reactions. In this particular case, when we use the methyl iodide in the presence of methanol, only 1 nitrogen is substituted, as quaternization happens on only 1 nitrogen. Whereas when we use this fluoroborate salt, we get the ethyl unit attached to both the nitrogen atom, that is the quaternization happens on both the nitrogen atoms. Next is the electrophilic reaction. So in this particular case, the corresponding pyrimidinium salt is treated with bromine in the presence of nitrobenzene as a solvent at a high temperature. The bromination, that is the electrophilic reaction, takes place. And for the nitration and the chlorination to occur, the presence of an electron releasing group is very essential. So unsubstituted pyrimidines does not undergo nitration and chlorination, but once the electron releasing groups like hydroxy is present in this particular pyrimidine ring, they undergo the nitration reaction as shown here. And in the case of a nucleophilic reaction, the nucleophilic attack takes place at 4, 6 and 2 positions. So basically the 4 position attack is the most favored one. So when we number it here 1, 2, 3, 4. So this is the 4th position. So the 4th position nucleophilic substitution takes place very readily. And when we treat with phenyl magnesium bromide, it gives the C4 substituted dihydropyrimidine, which aromatizes on oxidation. So when we start with pyrimidine, treat with phenyl magnesium bromide. The 4 position is the place where the nucleophile attacks first, and this undergoes re-aromatization by treatment with a strong oxidizing agent. If the 4 and 6 positions are occupied, then the reaction occurs at the 2 position, because 2 position substitutions are not very common. So unless the 4 and 6 positions are blocked, the reaction, the nucleophilic substitution does not take place on the 2 position. So this is an example of the nucleophilic substitution happening at the 2 position because of 4 and 6 positions are blocked. Then we also have the Unrock mechanism or the reaction, which we have seen earlier in the case of many pyridine derivatives and the quinoline and isoquinoline. The same reaction occurs here also. So when treated with KNH2, that is potassium amide, in the presence of liquid ammonia at a very low temperature, the ring opening takes place. Basically, the chlorine is substituted with the amine. So that is what is the actual reaction. But when we use isotope labeling studies, when the pyridine is actually having the isotopes on the pyrimidine ring, in the final product, one of the amine which is formed is actually having the radioactivity. In other words, the ring opened and the amide, the nitrogen from the amide actually is incorporated into the pyrimidine ring. So this is why this reaction is called aromatic nucleophilic reaction with the ring opening and ring closing. So here the ring opening takes place, and again this leads to further ring closing, and the nitrogen is actually moved from the ring position to the external position. Let us look at some of the chemotherapeutic agents. So imatinib is an anti-cancer compound. This is having the pyrimidine moiety as shown here, and lamivudine and reltagravir are all having the pyrimidine moiety as shown here. And sildenafil or Viagra is a erectile dysfunction drug, which is a very popular one, and it is also used in the pulmonary arterial hypertension related things. It is having a pyrimidine structure as shown here, and zidovudine is another drug which is used as an anti-HIV and AIDS agent. This is also having the pyrimidine moiety. Let us look at purine. Purine basically exists in 4 tautomeric forms. 1H and 3H are less stable. So here again, in the case of purines and pyrimidines, biologists are the people who actually started numbering them. That is the reason the numbering, as we mentioned earlier also, is not following the systematic number which we use generally in the organic chemistry. That is, the IUPAC nomenclature is not being followed here. So that is the reason. Let us start from the first one. So the nitrogen is having the hydrogen. So that is why this is called the 1H purine derivative, and this is a 3H purine derivative. The third nitrogen is having hydrogen, and this is a 7H position, and this is the 9H position. So these are all the various purines which are possible and which exist as a tautomeric forms, and 1H and 3H are actually less stable purine derivatives, so they are generally not isolated or found. And 7H and 9H are present in equal concentration in concentrated aqueous solution, and 7H purine is the dominant tautomer present in the solid phase. And how do we synthesize purine? The first method was basically by the Fischer method. So in this particular case, uric acid is treated with PCl5 to give the corresponding halo derivative. The trihalo derivative is formed in the first step, and because here this compound can exist in the ketoenol tautomers, that is the amide here, amide and the hydroxy derivative can exist as a tautomers, and when it is existing as a hydroxy derivative, all the 3 hydroxy can be replaced by the halogen. So that is why we get the trichloro derivative, and this trichloro derivative on treatment with HI and PH4I leads to the iodo derivative, diiodo derivative. One of the iodine is removed here, and this on reduction with the zinc dust leads to 9H purine as shown here. And guanidine, when treated with ethyl cyanoacetate in the presence of a strong base, leads to this corresponding pyrimidine derivative, because this is the one we have actually seen in the pyrimidine synthesis also. So the same pyrimidine is the starting material, and then this treatment with HONO leads to the nitroso derivative as shown here, and this on treatment with ammonium sulfide leads to the conversion of the nitroso derivative to the amino derivative, and this amino derivative on treatment with formic acid gives the corresponding hydroxy derivative, the cyclized one, and this can exist in the tautomeric form. Let us look at some of the synthesis of purines from pyrimidines. So 4-amino 5-nitrosopyrimidine as shown here when treated with formic acid in the presence of ranitidine leads to purine derivative as shown here. This is an unsubstituted purine derivative. Unsubstituted purine. We can also make the same from the 4,5-diaminopyrimidine. So in this particular case, instead of starting from the nitroso derivative, we can also start from the amino derivative. And if this particular amine is substituted with some group here as shown here, an alkyl group, then this nitroso group is reduced, partially reduced to give the amino derivative. Then the corresponding carboxylic acids can be used, and similar to the previous one, we can actually get R9 and R8 substituted, disubstituted purines can be formed. Next, let us look at Rcp synthesis. So here we have two different categories. One is preparing a 8 substituted purine derivative. Another one is a 8 unsubstituted purine derivative. So the only difference is we are starting with the diamino pyrimidine as shown here. This on treatment with acetic anhydride gives the 8 substituted purine derivative. The acetic anhydride, that methyl unit actually came from the acetic anhydride unit, and instead of acetic anhydride, if you use other anhydrides, then the corresponding alkyl group is present here in the 8 positions. And if we use formamide instead of acetic anhydride, we end up with a 8 position unsubstituted purine. And we can also do another method where acylation using acid halide can also be used for the same type of synthesis. That means starting from the pyrimidines, we have a multi-substituted amino derivative. This on treatment with the corresponding acid chloride gives the acylation on one of the amino group, and which on POCl3 facilitated ring cyclization leads to the corresponding aromatic derivative as shown here. So this is basically the acylation using acid chloride, and the isolation of the amide. We can actually isolate this amide, and we can subject this to the cyclization to give the corresponding purine derivative. That is again a 8 substituted purine derivative. The next one is the Bergman synthesis. In this particular case, amidine is treated with the corresponding starting material as shown here. This is nothing but the pyrimidine derivative. So the pyrimidine and this on treatment in the presence of acetic acid gives the corresponding, here if we start with the N-glucose derivative, then we also end up with the N-glucose derivative. So this is one method by which purine can also be prepared, that is a 9 substitution is possible. Another method is shown here. So here again the substituted pyrimidine is converted to the purine derivative. This reaction actually happens at high temperature and pressure under a sealed vessel. We can also prepare purines from the 5-amino-imidazole 4-carboxamide or from the nitrile derivative. So the carboxylic acid is treated with this is the amide unit, this is the amino unit, this is the imidazole unit. So that means the 5 position we have a amino unit, in 4 position we have a carboxamide unit which is present in the imidazole. This is reacted with the carboxylic acid, leads to the formation of this particular purine. And when we start from the same intermediate where the nitrogen is actually substituted in the imidazole derivative, we can also use isothiocyanate to form this kind of purine derivative, or we can also use anhydrides shown here leads to this particular product. Then formamide with POCl3 on heating in a sealed tube leads to substituted purine as shown here, and there is also another one-step method where these two reagents actually react together to give the substituted purines. And when we talk about the reactions of purines, basically the N-alkylation is one of the reaction because purine is having 4 nitrogens, so the reaction can occur at many places. So the first one is starting from purine, when treatment with methyl iodide in methanol at 100 degree gives the di-substituted, the imidazole ring gets di-substituted, and this is the product what we get. And when we use reaction with dimethyl sulfate actually gives the monoalkylated product as shown here, and in the presence of cesium carbonate and alkyl halides, any alkyl group or any R group can be introduced into this particular derivative. So these are all the various ways by which N-alkylation is possible. And when we treat the substituted purine with ethanol as the alcohol in the presence of diethyl azo dicarboxylate and triphenyl phosphine, that is Mishinnobu reaction conditions. So this gives the N-alkylated derivative. So in this particular case, we have the N substitution on this particular nitrogen or on the other nitrogen. So these are all the two different products that are possible. And in the case of electrophilic substitution reactions, the nitration leads to the 6 substitutions. When we have a 6 substituted purine derivative, the nitration of 6 substituted purine selectively happens at the C2 position as shown here. So this is nothing but butyl ammonium nitrate, tetrabutyl ammonium nitrate in the presence of trifluoroacetic anhydride basically gives the selective nitration on C2 position only. And another reaction is the Chichibabin reaction. So in this case again, the introduction of the amino group takes place in the presence of potassium amide and liquid nitrogen. So this again reaction is again a ring opening, ring closing mechanism. The reaction actually introduces a amino group into the purine. And when we look at oxidation reaction, hydrogen peroxide based oxidation gives the N-oxide derivative as shown here. And reduction can be effectively carried out using electrochemical means. So first we have the one carbon undergoes a reduction, that is one CN double bond undergoes reduction, and this leads to the dihydro derivative. Then we end up with the second double bond also getting reduced to give the tetrahydro derivative, and this on hydrolysis opens up to give this corresponding amino alcohol. Then let us look at some of the purine drugs. 6-mercaptopurine is shown here. So this is actually used for the treatment of leukemia and anti-immune diseases. Abacavir is another drug which is used for the treatment of HIV and AIDS. Fludarabine is another drug which is used for the treatment of leukemia and lymphoma. Let us now look at azepines. Azepines basically exist in 4 tautomeric forms as 1H, 2H, 3H and 4H azepines. 1H and 3H systems are more accessible and important. So the structures and the numbering are shown here. This is the 1H azepine, that is the nitrogen is having the hydrogen, and then this is the 2 position is having the hydrogen, and it is the 3 position where the hydrogen is present, and in the 4th position the hydrogen is present. So that is the reason the numbering is 1, 2, 3, 4. And when we look at the synthesis of azepines, this can be carried out using nitrine insertion on benzene. So this particular azide, sulfonyl azide, when treated with benzene under nitrogen pressure at a very high temperature, leads to this particular azepine derivative and other products. And we can also react a secondary formamide and a nitroalkene can be reacted together in the presence of a strong base to give the corresponding cyclized product. And we can also use alkyne to prepare azepines. So here the reaction of pyrrole and with alkyne is shown here. So this reaction is carried out in the dark, leads to the corresponding different isomers of azepine derivatives. And alkyne, amine and tetrahydrofuran can also be reacted together in the presence of PEG 400 at 60 degrees centigrade, gives the substituted azepine derivatives as shown here. And Carbamazepine is one of the compound. It is an anticonvulsant medication that is used primarily in the treatment of epilepsy and neuropathic pain. So this is the drug which is generally used for the treatment of epilepsy and neuropathic pain. Let us recap in the summary what we have studied so far. We have studied about the synthesis of pyrimidine. We had mainly focused on synthesis from malonic esters, Bedreich synthesis, Boltzmann-Rosch synthesis, Pinner synthesis, Remfry-Hell synthesis, Biginelli reaction, and Traube synthesis. We also studied about Purine synthesis, mainly focused on Fischer method. Then Traube synthesis and Bergman synthesis were also studied. And in the case of reactions of pyrimidines and purine, we studied about the electrophilic and nucleophilic substitution reactions. And-Roch mechanism also we had seen. And finally, we studied about azepines, mainly the nitrogen insertion reactions on benzene and from alkynes. How we can synthesize azepines we have studied. With that, we conclude this session. Thank you.